We'll now begin to explore one of the most commonly used statistical methods, linear regression. In many situations, the relationship between two quantitative variables can be summarized well by a straight line, our regression line. In this video, we'll examine how to find the line that provides the best fit to our observed data. Recall that we can visualize the relationship between two quantitative variables with a scatter plot. Our interest now will be in whether or not the relationship in each of these scatter plots can be summarized by a straight line. The line is an example of a model for the data. We can use the line to make predictions. For example, there's a positive relationship with the size of a house and its selling price. So, if we know a house has a certain size, we can predict what its selling price will be. Or we can use the model to investigate whether there is a relationship between the variables. For example, is consuming more fiber associated with lower blood pressure? A line can be completely described by its slope and its intercept. In statistics, the data points won't fit perfectly on the line, and the line is used to model the expected or mean value of y. The intercept on the vertical or y-axis gives the expected value of y when x is equal to 0. The slope tells us how y changes with x on average. A positive slope, like what we have in this picture, indicates that as x gets larger, y also increases. A negative slope would indicate that an increase in x is, on average, associated with a decrease in y. In statistics, the regression intercept that we calculate from the data is usually given the symbol b with a subscript 0, and the slope estimated from the data is given the symbol b with a subscript of 1. So then the equation of the line is y equals b0 plus b1 times x. This is often written as y hat equals the intercept plus the slope times x, where the hat on the y indicates that this is the value of y for the corresponding value of x that is predicted by the line that was fit to the data. Now let's take a look at a particular example. A study published in 1993 was interested in how the conditions that babies experience affects the development of their motor skills. In particular, the research asked the question, is a baby more likely to begin crawling earlier or later, depending on the season, as characterized by the average temperature when he or she learned to crawl? In this study, they looked at 414 babies. Our scatter plot includes a point for each of the 12 months of the year. On the horizontal, or x-axis, is the average temperature for the month when the babies were 6 months old, which is a typical age when babies first try to crawl. And on the vertical, or y-axis, we have the average age, measured in weeks, for when the babies could competently crawl. The plot shows a negative relationship. Babies born in warmer months, so higher temperatures, crawled on average at younger ages, perhaps because they tended to be bundled in less restrictive clothing. In this example, we're trying to see what effect the temperature has on the average crawling age. So the average crawling age is our response variable or dependent variable, because we're investigating whether it depends on temperature. Temperature is called the independent variable, or explanatory variable, or predictor variable. The response variable is plotted on the y or vertical axis, and the explanatory variable is plotted on the x or horizontal axis. Our data points are a set of 12 points. An x sub I for the average temperature in the ith month, coupled with a y sub I, the average crawling age for all the babies who turned 6 months old that month. We can model the relationship between temperature and crawling age with a straight line. The linear regression line for these data is the line that best predicts the response variable, the crawling age, from the explanatory variable, the temperature, in this example. So we want to minimize how far the data points are away from our line in the vertical direction, the direction of the crawling age, since that's what we want to predict. Sometimes these vertical distances will be above the line, so then positive, and sometimes they are below the line, so negative. These vertical distances or deviations are called residuals, and they'll be important to us in later videos. We can label these residuals E sub I, and E sub I is the difference between the data value for y sub I, minus the value predicted by the line, y hat sub I. We want to minimize the total of these deviations, positive or negative, so we square them, so then they're all positive, and add them up. This is called the method of least squares. In the method of least squares, the regression line is found by finding the line that minimizes the total of the squared vertical deviations from the data points to the lines. That is, we solve for the slope and the intercept by minimizing the sum of the square of the residuals. We can calculate the resulting slope and intercept from a few summary statistics, in particular the means and standard deviations of the response and predictor variables, and the correlation between the response and predictor variables. Recall, the correlation, often given the symbol R, is a value that's between -1 and +1, and measures the strength of the linear relationship between two quantitative variables. So it should be no surprise that the correlation is also related to the regression line. And indeed, the slope, which describes how y changes with x, is the correlation scaled by the ratio of the standard deviations. The slope can be calculated as the standard deviation of the y values divided by the standard deviation of the x values times the correlation, r. Remember that r can be either positive or negative, depending on whether y increases or decreases with x. A positive correlation will result in a positive slope, and a negative correlation will result in a negative slope. The role of the intercept is to shift the line to the appropriate location. To calculate it, we can use this formula in terms of the means and the slope. One thing to note from the formula for the intercept is that the regression line always passes through the point defined by the mean of the predictor and the mean of the response variable. And now, using these formulas and our summary statistics, we get that our estimate of the slope is about -0.14, and the estimate of the intercept, B0, is about 33.19. And putting that together, the equation of the regression line is the predicted crawling age is approximately 33.19 minus 0.14 times the average temperature. From the intercept, we know that when the average temperature is 0, we expect the crawling age to be just over 33 weeks. And since the slope is negative, our line estimates that, on average, for each increase in the temperature, we expect the crawling age to decrease by 0.14 weeks, which is about a day. To predict the average crawling age for a baby who experiences an average temperature of, say, 15 degrees Celsius, we can use the regression line to find the corresponding value of the response variable when the predictor variable is 15. And here we see that it's just over 31 weeks. But what if we wanted to carry out a reverse prediction? That is, what if we wanted to predict the temperature for, say, a baby who crawled at 32 weeks? Unfortunately, it's not as simple as rearranging our regression line to solve for the predictor variable given a value of the response variable, that is, solve for x in terms of y. Regression is not designed for that. Remember that we found our regression line by minimizing the sum of the vertical deviations. That is, we minimized how far our predicted values of crawling age were on the line from our observed values of crawling age. A line of best fit that would predict temperature from crawling age, the other way around, would minimize the errors in the horizontal direction, and we'd get a completely different regression line. That regression line is represented by the orange line in this picture. Modeling the relationship between two quantitative variables using linear regression, whether it's for prediction or to better understand the nature of the relationship between the two variables, Involves first clearly identifying one of the variables as the response and the other as the predictor variable, and then using the method of least squares to find the line of best fit. However, taking a first look at the data through a scatter plot, in order to determine whether a straight line model seems like a reasonable choice, should always be the first step. In future videos, we'll look some more at how to assess how well the straight line model fits our data.